All right. I want to introduce a webinar that I'm going to be doing Friday, April 15th. How to simulate and analyze ultrasonic bolt clamped Langevin transducers using modal analysis like an expert. So I'm going to be going through a lot of steps that are going to help you design and analyze ultrasonic transducers of this type, as well as many of the methods will also be applicable to other ultrasonic devices. I'm going to be talking about geometry simplification, how to get those pesky like piezo material properties. There's just so many of them. Which ones are relevant for modal analysis? I'll talk about a little bit about node and element count, different modes that occur. How do you analyze the output from modal analysis, which is going to be displacements and displacement mode shapes, and also um, frequencies. I'll talk about nodal points. And the thing I'm so excited about is how to characterize displacement amplification. How do you actually optimize a transducer in modal analysis? Because you don't really get a real displacement number output, you get a normalized output. So, how do you actually optimize a device with modal analysis, which is a most simple tool to do ultrasonic transducer characterization or in simulation? I'll also do this really cool thing where I'll show you how you can calculate the electromechanical coupling factor. The distance between resonance and anti-resonance also shows how well your piezos are coupled to your device. Um, how do you do that using modal analysis? I've only seen folks doing this with harmonic analysis, which takes a lot more time and it's a lot more difficult in order to get results. I'm going to be showing you how to use modal analysis, how to use this, apparently simple tool that many times people skip over and just go straight to harmonic. How do you use that for really impactful analysis? I'll also describe static preloading and according to also in comparing that to dynamic stress requirements. You preload your transducer in order to keep the crystals and all the interfaces under compression, and how does that rack up to the dynamic stress requirements? And finally, I'll give a cool thing, which will be the current draw estimation. Let's say you're trying to get a certain amount of displacement. What current would you expect? So you can get a lot of this information that you'd normally expect only to get from harmonic analysis. You can get that from modal analysis. It's going to solve a lot more quickly. You're going to have to deal with a lot less hassle in terms of many of the properties and analysis and settings as well. You can run more elements too. Go to the next slide. So again, this is going to be April 15th, 10 a.m. I'm going to have the link to register. It's already in the notes for this video. And some of the methods I will describe can be found nowhere else. And maybe some of these methods will also end up saving you a huge amount of time, confusion that you didn't have, confusion that you're having about simulations, like what piezo properties do I put in for the material, for example. And it will also allow you to really optimize your use of modal analysis, which is a really important tool. The link to register is there. Reach out to me in a comment here if you have a question about this event. But it's going to be over Zoom. It's going to be a public event. It will be recorded, but there will only be, I guess, the instruction be the only thing that's recorded. The question and answer session will not be made public there. So register, come and really optimize and up level your understanding and use of modal analysis. Again, my name is 𝐬𝐤𝐴𝐻𝐿𝐼. I am the founder and lead consultant of my company, Ultrasonic Advisors, where I help companies with simulation, optimization of ultrasonic transducers, as well as providing hands-on and advisory support for a whole host of problems and challenges that ultrasonic transducer teams typically will go through. So I look forward to seeing you at the event. It's Friday, April 15th, 10 a.m. Eastern. And don't miss it and tell your friends about it. Thank you.